we're going to keep talking about angular momentum, which is the last big thing. And even though it's not on the test, this is actually, it's going to be on the final, and this is really important. So angular momentum tends to be slightly overrepresented on the final because we don't have a chance to give you a test on it. As we talked about last time, angular momentum, basically, it's the thing we've all been wanting to measure going aroundness, so that the kid going around at constant speed on the Ferris wheel, the direction of the momentum's changing, the direction of position is changing, but the angular momentum is constant, and it involves both position and momentum. Angular momentum is probably so far the most abstract quantity we've encountered here, because angular momentum is a vector. It's got a magnitude and a direction, but there are no atoms moving in the direction of angular momentum. So momentum, atoms are moving that way, velocity, but angular momentum, there aren't any atoms moving in the direction of angular momentum. And there are two, so it's about going around, and there are two kinds of going around. So there are two kinds of angular momentum. There is there's translational or orbital angular momentum, and there's rotational or spin angular momentum. And the thing to think about is the Earth going around the sun. So imagine, you know what it looks like. A picture of this would look like. Here's the sun. Here's the Earth going around the sun. Okay, the Earth is orbiting the sun. So the center of mass of the Earth is moving. And translation has to do with motion of the center of mass. So we call that kind of angular momentum translational angular momentum. The center of mass of the Earth is moving. Or it's also called orbital angular momentum. You may know that name from chemistry because it's something orbiting around a center. But the Earth isn't just doing that, right? It's also rotating around its own axis. Well, that's angular momentum too. And even if the Earth weren't going around the sun, if it were just sitting in space, but it were spinning around its own axis, it would have angular momentum. So that kind of angular momentum is called rotational angular momentum or spin angular momentum. So there are two names. So we have translational or orbital angular momentum and rotational or spin angular momentum. And this rotation, we mean rotation around an axis that's going around the center of mass. And we give these things different names. So angular momentum has the symbol L. It's a vector, as we talked about last time. And I don't know why it's called L. Same reason momentum is called P, I guess, but because there's no L in, yeah, well, there's angular. Okay. So the translational angular momentum we write as L A translational, and this, remember, this A has just identifies the point that we're considering as the center of the motion. So if here's location A, that's the vector from R sub A from location A to the object of interest. Here's the momentum of the object. It's moving around the center, and so that's translational or orbital angular momentum. You can call it either. They're both correct. And then rotational or spin angular momentum is this. So this is relative to some point A, and this is relative to center of mass and axis. And so not surprisingly, the total angular momentum of some system is the sum of its translational plus its rotational angular momentum. So the first thing we're going to do is just get a little more familiar with this. We'll calculate translational angular momentum of some system. We'll calculate the rotational angular momentum. We'll add them together, make sure we understand what these are. It is important to understand these concepts. You can't make much headway working problems using these concepts if you don't have a conceptual understanding. So let's make sure that we're really all on the same page about this. And eventually we're going to get to a principle, and it's going to be a really familiar looking principle because it's going to say that angular momentum is changed by some input from the surroundings, and in this case it's called a torque or a twist. And so it's going to look really parallel to the momentum principle, actually. And we'll write it in different ways. Although we can calculate, we have two different ways to calculate this translational angular momentum. So we said that translational angular momentum was given mathematically by the vector cross product of this vector r from whatever location A is to the object of interest and the momentum of the object. And that's the full vector mathematical statement, which sometimes actually is the easiest thing to use. And remember that so this is a vector which has x, y, and z components, and following the rules for vector cross products, the x component, if r is some vector x, y, z, and p is some vector px, py, pz, then the x component involves y and z. Remember, there's this sort of cyclic relationship, a mnemonic for remembering how things go. So the x component is y pz minus z py, and the y component is z px minus x pz, and the z component is xpy minus ypx. And that's not as bad as it looks, because remember that when you take a cross product, the two vectors of interest define some plane. Any two vectors, unless they're in a line, but define a plane. And the cross product is perpendicular to this plane. So the necessity of figuring out which direction it is if you can identify the plane, then it's either one way or the other. That's all you have to resolve. We also had a way of finding magnitude and direction separately, because, and we're going to work on this a little bit, because even if you can evaluate this really easily using determinants or just remembering this, you need to check your answer. And the way to check your answer is to make sure that you've got the direction of your resultant vector correct, because that's where most people go wrong. We did see that the magnitude of the translational angular momentum was given by the magnitude of r times the magnitude of the momentum times the sine of the angle between the vectors. What's the angle between these two vectors? Well, to find the angle between two vectors, you have to put them tail to tail. So step one is we redraw them. There's R, and P was kind of like that. So, and then the angle between them is the smaller of the two possible angles, so that's the angle between them. How do we get the direction? So that's a way to get magnitude that sometimes is easier if you happen to know the angle. If it's not, this is going to be easier. In either case, you need to get the direction, and the direction is given by the right-hand rule. Often abbreviated just R, H, R. And the right-hand rule, what you're going to do is point your fingers along the direction of the vector that comes first. This is not commutative. So when we say first vector, we mean the one that's written first. That's vector 1 and that's vector 2. So you're going to point your fingers along that direction. Then you're going to curve them toward the other vector. Your thumb will stick out. But it's not as bad as you think, because there's another step, which is first you draw tail to tail. We did that. The next thing is now you get to rotate this whole assembly in the plane until it's actually easy to point your fingers in the direction of R. Without changing the angle. So it's easy to align your fingers with R, or with the first vector. Because the cross product is going to be the same no matter where these vectors, how these vectors are oriented. So if we oriented them this way, as long as we haven't changed that angle, the cross product is going to be the same. So what we're going to end up doing is we're going to point our fingers in the direction of the first vector. We're going to bend them through the angle theta until they're aligned with the second vector, and then our thumb is going to stick out in the direction. So fingers are fold through the angle theta, and your thumb sticks out in the direction of R cross P. But sometimes it's just kind of awkward to do, so you don't actually have to do that to get the cross product. You're actually allowed to make it easy for yourself. So just imagine, draw them on a paper and turn the page, whatever you need to do, until it's actually comfortable to align your hand with R and rotate through the angle theta to get to P. Now, what could happen that could make it go wrong? Well, suppose you had vectors that we had. Here's R, and suppose when we got all done, we discovered put them tail to tail. Angular momentum was like that. That's still the angle theta. But now we have a problem, because if we point our fingers in the direction of R, and we can't, no floppy wrists here, that's why we want to rotate these till it's comfortable, then we're not set up to rotate our our fingers through theta. So we have to actually turn our wrist over so we can do that. And then the angular momentum is into the board. And there are two symbols for into and out of the page that are helpful. This is into the board or the page. Think of it as an arrow whose tail feathers are arrow disappearing into the board, you're seeing the tail feathers. Whereas in this case, L is out of the board, and that's the tip of the arrow coming at you. So you need to remember those symbols. And we might have had an easier time if we'd actually rotated this a little bit more, so it was a little easier. So we might have chosen to rotate it so that R was up and momentum was that way and theta's that way, and then it's really easy to do it. So that's how you do it. And we're just going to practice a couple before we go on and do something interesting and useful with angular momentum. So first, let's actually just think about a really, really arbitrary cross product that doesn't have anything to do with angular momentum. Okay, so the vectors that we want the cross product of are 0, 0, 3 and 0, 4, 0. Okay, so what's the direction, just the direction of that cross product? So try to visualize those vectors. You can draw them. You can crank it out here, but just see if you can think through it without cranking through it here. Okay, well, the good news is that most people think it's either plus or minus x. But we need to know which. Now, how do we know it's going to be plus or minus x just from looking at this? What plane is defined by these vectors? The yz plane, isn't it? This one is on the plus z axis, that one's on the plus y axis. So the vectors are like this, aren't they? So the result, the cross product has to be perpendicular to the yz plane, which means it's either plus x or minus x. And now we need to figure out which it is, and for that we need to get straight how we do this right-hand rule. So we're going to point our fingers in the direction of the z-axis. Now that's easy for me. You might want to redraw this. Okay. So here's vector 1. That's the plus z-axis. Vector 2 is here, so we want to curl our fingers up. Notice that I couldn't do it without rotating my wrist. Okay, I can't do that, so I've got to rotate. That means my thumb sticks out that way, which is negative z. Okay, negative x, sorry, negative x. So 2 is the correct answer. Okay? Questions? So what's the direction of 040 cross 003? Right hand, not left hand. If your pen's in your right hand, yeah. So this is one where people who are left-handed have a big advantage because they're holding the pencil in their right hand, so therefore they're holding the pencil in their left hand, and therefore they just use their right hand. But if you're right-handed, you want to make sure that you're actually not using your left hand. And that is correct. So it's plus x. So the first vector is 040, so our hand goes up. That's easy. And the second vector is 003, and that means our thumb is sticking in plus x. So it really isn't commutative. If you do it backwards, you get the wrong answer. Okay? So yes. Well, okay. So you're gonna be. So how do you know which way to turn your hand? And it's trial and error. But so here I'm pointing my, so 040 is up in our usual coordinate system, right? The next vector is 003, pointing out toward you. And the rule is I don't have to break my fingers. So even if I had my hand this way to start with, when I realize I can't do it, I have to turn it around and do that. So here's the plane, right? One vector that way, one vector that way. So you can use the edge of your paper to help you. So here's the YZ plane. So first vector, oops, second vector, all right? So how do you know which way to hold your hand? You guess, and if it's wrong, you turn it. But since there's only two possible ways, it's not a big decision. Okay, all right? We good on that? Fine. One more. Okay, 006 cross 00, negative 3. You didn't get trapped. Good. Okay, so with these two vectors, one's on the plus z-axis, one's in the minus z-axis. So already we should worry because that doesn't define a plane, does it? It just defines a line. And that means that we can't find a vector perpendicular to a non-existent plane, which sends us back here to this form where we find the angle between them is 180 degrees. What's the sine of 180 degrees? 0. Or this form. So we have the x component here of the resultant vector would involve y and pz. Well, that's 0, and that's not. That's not 0, but that's 0, so the x component is 0. The y component, well, that's 0, and that's 0, and the z component, there aren't any z's, so everything's 0. So any way you look at it, it's just the vectors are collinear. It's going to come out to 0. Okay, one more thing, and then we'll move on. Let's try this. There we go. Try this exercise using this definition, R cross P. Okay, you know how to get this one by just curling your fingers in the direction of rotation, but do it the other way. Okay, do it by drawing the vector R in your mind and R cross P, and then using your right hand to work it out. Okay, so people say 5, which is plus z. So let's see how we got that. We're in the xy plane, right? So it's going to be plus or minus z. We do have to envision r, though. So here's r sub a, because a was the center of the sun. That was p. Now we have to draw the vectors tail to tail. So here's r, and there's momentum. And now we see that the angle between them is going to be that angle. So we might want to rotate it so it's up, so it's easier to do, but this isn't too bad. We can do R cross P, and indeed, you get plus Z. And that's consistent with the informal. Okay. Questions about this piece? All right. So let's calculate the translational angular momentum of the Earth as it goes around the sun. So what do we need to know? We have to define some coordinate system. So we'll say it's doing it in the XY plane, just to make our life simpler. But what else do we need to know? Okay, so here's the Earth. That's the sun, actually. Sorry, here's the sun. Where shall we put the Earth? Somewhere, it doesn't matter, right? Here. And so now that's the vector r. How do I draw P? More or less perpendicular, right? Because it's very close to a circular orbit. Okay. So what do you want to know? Magnitude of r. Okay, what's the distance from the Earth to the Sun? It seems to be 1.5 times 10 to the 11 meters. What else do we need to know? Mass of the Earth. Okay, mass of the Earth is 6 times 10 to the 24 kilograms. Thank you. Okay, what else? Oh, the speed. Oops. It's not in here. How do we get the speed? Goes all the way around. Okay. So the speed is going to be 2 pi r divided by 365 days. Good, but that's not SI units, is it? 365 days times 24 hours in a day times 60 minutes in an hour times 60 seconds in a minute, which comes out to? Okay. What comes out to that? This or V? Times what's the whole thing is? 3. Well, that was, yeah, this is actually, comes out to pi times 10 to the 7th pretty much, I think, doesn't it? Actually. Anyway. So this comes out to some number, which is actually probably, since it is worked out in the book, we'll look. 39885 meters per second. So 3, 2. That's way too many significant. 29885 meters per second. We're going to call that 3 times 10 to the 5th meters per second. 4th. Okay. So what's the magnitude of the angular momentum? The orbital angular momentum. So we have 1.5 times 10 to the 11 meters times 6 times 10 to the 24 kilograms times 3 times 10 to the 4th meters per second, which is well, it looks like there's going to be 11 plus 24 is 35 plus 4 is 39. 2.7? 2.7 times 10 to the 40th, and the units are going to be, looks like kilograms times meters squared per second. What about the angle in between them? Good point. Well, we better write it down just to keep ourselves honest. So we have sine of 90 degrees here, because sometimes it isn't a right angle. That one. Okay,